Okay, so we're going to shift focus somewhat to look at simulation modeling at the facility level to try and find pathways for net zero. Duncan, really, over to you. Tell us what this is and what you can deliver.
Thank you. Yes, thank you. My name's Duncan Mitchell. I am at KBC, where I am the Global Head of Decarbonisation. And it's got an S. My badge says is a Z. My observation is we can't even agree on how we spell it. The other thing I was remarking before, thinking about my comments, is the word summit. We are at a Decarbonisation with an S Technology Summit, and I was thinking about the word summit, and I think perhaps it's got something to do with the fact that this is something we all do on top of our day jobs. So if you'll forgive me, I'm then going to talk a bit about how KBC is working globally using modeling software to look at emissions, particularly in the refining and petrochemical industries, and to talk about perspectives on how that might help expedite the path forward to net zero. And there it is with a Z. It looks weird, doesn't it? Okay, so we are basically working along 3 time frames, and I'll talk about each one of these in a minute, but I just wanted to give you a frame for how we think about taking our clients on the journey to net zero. And you know, it really starts with figuring out where you are right now, figuring out what your emissions are, and why you're emitting those emissions. Then what we do is we work with our clients to build a sort of this whole simulation framework or some toolkits around what can be done about these emissions. And then it's basically the long march. We break it down to 3 pieces, and I'll talk about each one of these. There's getting started, if you haven't already, and getting on with your emissions reduction stuff you can do now. Quick wins, we call them. Bit of a consulting term, that. But nonetheless, we've got quick wins. Then then it starts to run to money. I think Spike Milligan and the Goons said that back in the 50s. That's going to run to cash, and that's what it's going to run to. And then we've got realignment, which is what is the future of this, in this particular case, the fuels and energy industry look like, and petrochemicals. What does it look like by the time you get to 2050? But we can't sort of spend all our time staring at the end of this. So my comments will be focused mostly around the beginning. What can we do now? And as I said, we're going to look at what energy management systems can do. What I was kind of proud of myself for this one, GPS navigation. We have a product called PetroSim, which is our modeling, process modeling tool, which is going to be the core of our road mapping that I'll explain to you. So GPS means guided by PetroSim, little plug. And then finally, though, I think some of the most exciting stuff, and we heard about them this morning, is the whole piece about networks and what we can do by thinking outside the box, beyond our battery limits, and how collaboration between companies, it will also take us all on this journey to net zero. So starting on the first part, I'm going to talk a little bit about how we use some of our technology, but it's not about our technology, it's more about how you can use things like energy management systems to get a handle on your energy and emissions journey right now. So this is all about getting organized about your information, getting organized about your compliance reporting, getting organized about your credits, your taxes, and just making sure you got that information, you're using it properly, you're applying it to the right places, and then in particular, how you can use that information to actually reduce your energy bill now, and therefore your emissions. And so unhelpfully, this is, I'm going to go to the end of this. So energy management systems, that first part I was telling you about, we break them into two parts, as I did just then, which is to say there's a whole piece around emissions accounting and reporting. There are tremendous, and there are going to be even more regulations about when to report, how often to report, the accuracy of those reports, the units that you report, and it's going to be globally different. So you're going to have one set of regulations in Europe, you're going to have one in Asia, you're going to have one in the US, and they will unhelpfully be in different units and with different things emphasized. But nonetheless, the solution is going to be around some sort of information gathering, information distillation, and then for report preparation and all this. We have a product that we call Visual Mesa. Understandably, it's a visual software product. It helps visualize information flows. It helps visualize data, and we use it to look at anything from Scope 1 tank emissions, Scope 3 supply chain emissions. We use it for dashboarding. We use it for even operational reliability. So those tools are available. The second part of this energy management system is another exciting piece, which is using that information to optimize the supply of energy. So this is an example of the first piece, the energy management system, of the visualization of energy. And here you can see how, in this particular case, you start with an aerial, a satellite image perhaps, or Google Maps of your facility. In this particular case, I believe this is a Standard Fuels refinery. And you can actually map out where each one of your emitters are, for everything from the utilities to your individual units like a hydrocracker, your flares, and you can measure not just your CO2, but your carbon monoxide and your SOx and NOxes and that sort of thing. So this is just collecting information. It's not doing anything with it at this point. It's just presenting it in a visual way that allows people at the operating level all the way up to C-suite. Again, another consulting term I hate, but I use it. So this is what an energy management system, that's what a modern energy management system looks like. We find that globally, some of our clients are very mature in this, and they've been doing it a long time, particularly in operations, but perhaps less so on emissions. So a lot of this journey is to say the same discipline you apply to a dollar and a barrel is the same thing you should be doing applying to for emissions. And so this system and systems like this do just that, drill down from a very high level to a very practical operational level. I should check to make sure these things aren't animated beforehand, shouldn't I? Oh, but this is the other piece of that puzzle, which is, okay, you got the information, but is there something you can do with it? And this is an example of using the information to feed back to operations to say, what can you do to improve your supply of energy and thereby reduce your emissions? There's a real example of a refinery in Europe. Each one of those dots is a data point taken from the management system to say, was this the use of energy and therefore the emissions from this energy, and I'll go into that in a little bit in a minute, but was it optimal? Could it be improved? And in this particular case, we set up the system, and the idea was the opportunities to improve the mix of energy, whether it be fuel oil or steam or fuel gas, electricity, shaft work. It's looking at the complete supply of energy to this facility. Could it be improved? And how could it be improved? So the system was installed, but before they actually started feeding the information back to the operators, they ran it for a while to see just what the improvement opportunities might be. And then they turned it on, and you see the step change. Mm-hmm. So as soon as information was fed back to operators about how you could tweak the current energy supply and therefore the emissions, they were able to take, this is open loop. So in this particular case, a human sees a report, sees a screen, and takes action. And like I said, each one of those dots, this thing's doing it every 15 minutes. Humans can't respond this quickly. They've got other things to do, and they need to be guided. So an energy management system allows very quick focus on opportunities to improve things. And you can see what happens over time. It continues to improve. As they fix one thing, other things come up, and then the amount of opportunity to the perfect situation, if you wish to call it that, improves over time. So that's the first thing you can do. Now I'm going to move on to GPS navigation, guided by Petrosim. So the first thing I talked about was what you can do right now to a plant that's operating just with current equipment, current operations. We didn't change anything except tweak whether you're using more steam, electricity, fuel gas, fuel oil, that sort of thing. No change, wouldn't be a noticeable change in output. But what we do now, as we look forward to what you can really do to hit your targets, is to start looking at mapping real, true, deep reduction. Because what we're doing here with Petrosim is we're using the last piece was about the supply of energy. Can you improve the supply of energy to reduce emissions? It didn't ask about, are you demanding the right amount of energy? So what we do now with our process models is to ask, what is the optimum demand? How can you improve the demand for energy? And that's about energy efficiency. I'll get into that in a second. But it's about matching the demand for the energy from the refinery, the petrochemical plant, the upstream, any plant that uses energy, and how you're supplying that energy, and marry the two. And can that be optimized to reduce emissions? And that's what we're doing with what we call the IP3EM. No one's ever going to give us prizes for creative names. That just stands for the Integrated Process Energy Emissions and Economics Model, because it brings all those pieces together in one and visually displays to you what your opportunities are. So this is just a summary. This doesn't come from the model, but these numbers are generated by the model. The first important thing is embedded in that model, we have our knowledge database of just how much energy things like FCC units, reformers, crude units, vacuum units, alkylation units, your classic refinery, fuels refinery, or even aromatics refinery. We can do this for petrochemical facilities too. And we can actually map where the energy is being used and how that energy is on an efficiency based on a comparison of global performance. Who are the best in the business? Who are the laggers? Where do you stand? And we can look at a process level and say, this is how you stand. And if you were to improve and to be the best in the industry, this is what your emissions would do. So there are two exciting things here. Well, one exciting thing, good news, bad news sort of thing. The good news is, depending on how bad you are right now, the worse you are right now, the better the immediate opportunities to improve your performance, right? That's the good news. I guess the two pieces of bad news. The first piece of bad news is a lot of people have been focused on this, particularly in Europe, and the US in particular as well. They've been focused on energy, so there's less juice left in that orange. So we've got more. The gaps between the laggers and the best in class are shrinking. But this is probably the most disappointing news, which is even for a woeful performer, you're not going to get much beyond a 25% reduction in your emissions. It's just not possible. Mother Nature is standing behind you, pointing the finger of equilibrium at you all the time. Right? There's just so much that thermodynamics and process kinetics will let you get away with, and it's probably a maximum of about 25%. And that's assuming you're bad. For the good performers, it's even less. So when refiners come to us and say we want to reduce our Scope 1, Scope 2, what should we do about it? The first thing we look at is energy efficiency, and we do an analysis, or they may have one already. There are plenty of energy benchmarks out there, and say, hey, it's going to get you 10%. Now that's not too shabby. This is a 150,000 barrel a day refinery modeled in our process. We tweak these models to be actual specific to your facility, but this is a generic fuels refinery, and it's operating third quartile, which is why I put the base there. And it's releasing about 221 tons, just over 220 tons an hour, Scope 1 emissions, CO2. So it's a 10% reduction is going to be like 180,000 tons of CO2 a year. Not too shabby, right? 10%. And that would get them down in the second quartile, which is probably achievable with some minor capital and some reconfiguration perhaps, maybe some heat integration studies, but it's very possible. How am I doing on time?
You're okay.
But to go beyond that 20%, to go beyond 20%, you're going to have to start taking some active capital projects. And what I did was I looked at, this model allows us to look at what those capital projects might look like. And in this particular case, just for giggles, I said, okay, let's just take one of the largest emitters of CO2, which is the fired heater on the crude and vac, and said, hey, here's some things that everyone's talking about. Let's electrify the thing. Now, I know we've got some people here who do electrical heaters, and I'm reasonably assured that electrification of heaters is very much a possibility and coming soon. We're seeing it more and more. But the news is, if you just went and electrified that heater, sure, you'd get rid of that 37 tons of CO2, clearly you would. But if you just bought more electricity off the grid and didn't care where it came from, your Scope 2 emissions go up way more than your Scope 1 emissions go down. So you've got absolutely nowhere. I'll give you an example. I was at a biorefinery in Singapore last week, and we had this discussion. And the guy said, they want me to electrify that heater over there across the parking lot. And we all looked out, and there's this beat-up old fired heater. And he said, look at that thing. And but they wanted me to electrify it before I rebuild it. So we went and did this whole project and said, yes, we can electrify it. We can go ahead and do that. Called up the local power station and discovered that actually their Scope 2 emissions would go up more than that particular fired heater would save. Mm-hmm. I don't think this is rocket science. I think people get that. It's why you don't electrify right now without getting green electricity or low carbon intensity electricity. But this goes to show how modeling helps you spot that before someone at the high level is asking their engineers to do a study on a fired heater that makes no sense from the get-go. Let's do the same thing with hydrogen firing. If all you did was ran natural gas, quite apart from the fact, by the way, that hydrogen is 20 times more expensive than natural gas to fire right now. Again, technically very feasible. You can go to 60% hydrogen firing on a fired heater now, just by changing the burners. 100% if you rebuilt the heater. But if all you did was run your SMR harder or build a new SMR and put in gas you're buying off the grid, look what happens. Your SMR is chucking out more CO2 than you're saving in that fired heater. So again, you're going backwards. So purely thinking about projects in isolation is not a good idea. It needs to be studied, needs to be thought about as an integrated, which is the I of the IP3EM, it needs to be integrated into your overall plant plan. And then finally, some good news on carbon capture. Well-established technology, has been around for decades. MEA, as John was saying, well understood. People have got all sorts of, there are probably as many different amines now as there are colors of hydrogen, but they're all going the same place. The good news is you actually do reduce your emissions, but for in this particular case, I took 33, I said 95% efficiency on the removal for this. And I said, hey, what happens if they put an amine system on the flue gas from the again, the crude vac? It does reduce the emissions, but unfortunately you're giving a lot of it back, giving about 50% of it back. Why? Well, because you've got all that steam that John showed going in the bottom, regenerating the amine. Where's that coming from? It's coming from the boilers. What are the boilers firing? They're firing gas. Where's that CO2 going? Out the stack. So it becomes a bit circular. You give some of it back there, but the worst piece is the flue stacks are atmospheric pressure, obviously. All right? To move CO2 anywhere, you need to compress it, something over 74 bar to put it into critical phase. Right? That's a heck of a lot of compression. Right? We're talking here 33 tons an hour of CO2 to be compressed. So if you, again, just buy that electricity off the grid at your current carbon intensity, you're giving a whole bunch of those emissions back. Okay, so my point here is not to tell you this is all doom and gloom. It isn't, because obviously if you've got low carbon intensity electricity, this makes a bunch of sense. If you've got access to green hydrogen because you've got a bunch of electrolyzers, this could make a bunch of sense. But purely just switching over now without thinking about these things doesn't make a lot of sense, or has to be considered carefully. And even then, we come down to carbon capture. What are you going to do with all that CO2? Mm-hmm. Right? This just compresses it and sticks it in a pipeline locally. It doesn't get it anywhere. Okay, so I just wanted to say that we're doing this. Each one of these bubbles starts. We're right now. We've developed these models, and we're actively working with clients in Europe on refinery fuel refineries. We're starting to apply this technology to upstream, to use it there on gas plants, and even in upstream flaring. And we can apply it to olefin crackers and aromatics plants.
3 minutes left.
All right, let me just wrap up, because I do want to say we've heard about networks. So what we're also doing now is to apply. Let me just skip ahead. You might. This is the same Visual Mesa tool that before I was just using within a refinery boundaries and helping to look at compliance and look at information systems and dashboarding and compliance and reporting and that. This is, we're now starting to apply these energy maps to much bigger systems. We've got some discussions that are nationwide to start looking at how does a system look at its grid, where has it got wind and solar, where has it got electrolyzers switching over, how can it optimize that whole system? Because the same optimization applies, it's just you replace an M with a G, megawatt to gigawatt. So we're starting to look at that, and we're also starting, we as KBC find a lot of what we do, we're not licensing technology, we're not licensing electrolyzers or refining technology. So we tend to play an independent role where we try to come in and act as brokers of information between companies who are looking to solve things. So, we're starting to apply that Petrosim modeling to biorefineries. This is an example of SAF and renewable diesel production from a whole range of renewable fuels, renewable feedstocks here. So we're looking at, and then we can use this and blend it into our refinery models to see how it would fit in. And then finally, this is just a thought provoker. Using that energy database I told you about at the beginning, we can show that 2 refineries that operate at 50% capacity are 10%, nearly 10% less energy efficient than the same refinery running at 100%. Why does that matter? Well, this is Konkawi's predictions of the future of refining utilization. It's not pretty, again, I don't want to be all doom and gloom here, but the future of utilizations, particularly to make fuels, is dropping, as would be expected. So do each one of those refineries just peter out individually? Well, the answer, of course, is no. Of course they don't. They have to start working together and combining capacity, because it's much more efficient from an emissions point of view if they said, okay, let's just shut down one and let's run 2 of these virtually. So what we are doing now is starting conversations with multiple refiners who traditionally would never talk to each other. But as independents, we step in and start forming networks to say, are there better ways of doing this? Can we provide some independent and dispassionate, unbiased opinion using models that are credible and using information that you provide us to sort of figure out if there's a better way? And I think this is the, as I said, I was in Thailand a couple of weeks ago and starting this conversation about a couple of petrochemical plants and an onshore gas plant and a couple of refineries in the same area to sort of say, have you started having these conversations? Would you be open to it? They've got to be careful, even in Thailand, but the conversation is starting to move in that direction. And eventually, the idea is you put together enough thought, you're not going to do it without a government role. Someone has to step in. That's because this is all losing money. A carbon capture plant starts at $500 million, $500 million for an amine unit. I mean, this is serious money. So the point is, these guys are going to put together projects, but they're going to have to go to the government and say, we need you to sort of make us whole because we're not going to do this. We're not going to lose money. If it's about losing money, it makes anyone understands it's better to start losing money next week than it is today, right? So unless someone comes in and says, let's figure out how to get you guys moving, it's not going to happen. So that's another role we're playing. And again, it's the role of digital simulation that allows you to say, what if, before you've actually put $1 down. I think that's about it. Oh yeah, this is an example of a complicated network we're doing in Japan as well with the same sort of approach. So we're going beyond refiners, but we're now looking at power plants, steel plants, and looking at the energy grid of the whole thing. All right, I won't summarize it for you.
Fantastic.
There we go.
Thank you. Take your emissions as seriously as you take your operations. Yes. And the governments will be doing so too as they convene those conversations. Any quick questions before we go upstairs? John. Any other takers?
Yeah, very, very quick question. John Gibbons, Sheffield UK CCSRC. What do you do about this electrification sort of problem? Because just by definition, if you use a bit more electricity at the margin, you're already using all of the zero marginal cost stuff you can get your hands on. It's bound to be fossil. And at the margin, it's bound to be unabated fossil. And that will be the case, forever, basically. What do you do about that? So you can always make that argument you're making. It will always be true. But equally, we do want to electrify.
Yes. Obviously, electrification will have a role. All those technologies will have a role, and new technologies that we haven't talked about and don't even know about will come out. But I think it's a dirty word in Europe, but I will use it anyway. Nuclear, right?
Yeah, but even nuclear, you can't build it before it's needed when you don't want to.
But you've just said there's a bunch of baseload coal. So
Baseload coal. I said there's coal actually that's two shifting or less. And there's gas that's two shifting or less. But any time you say to the grid, give us a bit more electricity, the short-term response is always fossil at the margin.
Yes.
Short-term response.
Yep.
So, but then obviously there's a long-term response, build nuclear.
Right.
When you get over this thing, someone can always say the short-term response is fossil, but there's a long-term response.
But there is a hurdle, I think, for things like electrification. But there's also a hurdle on CCS. How does how do you get enough people interested in making a CCS plant? And an offshore sequestration project going. There has to be a hurdle which you get enough people interested or you get enough demand, and to do that you need to go around, and it's not going to be one plant, it's going to be collections, it's going to be networks, is what we saw at HyNet and what we see in these projects. It's going to be clusters. So you've got to go around and say, okay, if enough people do it, then you have enough demand to make a difference, to start moving the needle.
And if
I think it's the only answer you can have.
if I may come in, you know, all of the demand response flexibility in the electricity system, I think this might be a question for a discussion another time, because there are some electricity people it would be great to have in the room who've been working on the other end of that. And it's been fascinating to hear your end of the question, because I think the electricity sector has far less understanding of this than it would need. A question over here.
Hi, Thomas Herod-Taylor, Head of Digital Engineering Platforms at Carbon Clean. How do you integrate your model into the digital ecosystem of your customers?
So we do that in two different ways. I mean, obviously we have the energy management system, which is used to be optimizing, and therefore it goes into the day-to-day management of the plant. All right? Does that answer your question? Because the second part is, for the longer term, we build business models with their own refinery models to sort of say, this is what this means for you.
What I mean,
I think I missed the question, didn't I?
That's part of the question, part of the answer. When you talk to different customers, they will have, within a network, one customer will have a model in, say, Aspen HYSYS, one will have another, Aviva and so on, and you've got KBC. How do you integrate all of those models together to leverage value for customers? How do you work in that ecosystem with multiple customers to derive value?
So the Visual Mesa system is system agnostic. It just pulls information out of a PI system, whatever system you have. If you get into detailed analyzing of specific plants, and we don't do steel plants, for example. So if you've got a production plan for a steel plant, we take that as a black box with emissions factors and energy factors. So that's how we start. If we're going outside a refinery, if we're just talking about refiners, we would probably build a multi-unit, multi-plant approach to the solution. Right now, my approach was purely ISBL, inside the battery limit. So, but you do need a refinery-wide model to do that. A lot of our customers do, but if not, we take our generic model and we adapt it quickly to their specific plant. And then we can be broad about that. If you've got an olefins cracker built in, you've got an aromatics plant, we can build that in as well.
Okay. We'll get into trouble on the schedule if we don't.
Yeah, everyone.
Robin,
go
on. Robin, you're special. Go on. Quick one.
Duncan. So I'll pick up afterwards. But there's a big difference between modelling for refineries or with a hydrocracker and just totaling their hydrocracking capacity, etc., versus actually how do you optimise for different refineries with subtotals, etc., so that you were looking at how to optimise 3 refineries, but then you have to make some assumptions on how you load those individual units. Yes, we had this conversation actually yesterday. Patrick and I we had a conversation in Rotterdam about this. So we have yet to cross that bridge, but in our minds, you don't need a detailed refinery process model with yields for an emissions map. So we can get away with a certain amount of simplifications because we know where the main emitters are and we know what the main energy users are, so we can focus on those and ignore some other parts. And that's probably the way a multi-refinery site would look. And the idea is that one of the ideas being batted around is, the refineries make their own plan, optimize their own operations, and then it gets uploaded to a master plan with those constraints in it, and then you optimize the big scheme for minimized emissions. So they still get everything they want. They've optimized everything they want for their own needs, but then a bigger model with slightly dumbed down to be otherwise it won't run, but it is running at the higher level. Yes, Patrick.
If I can add to that a little bit, is that, I think what you're referring to this discussion, and we're talking about innovation, this is one of the innovation discussions we're having with industrial clusters. It's not that we've combined things together, but we are opening the discussion. Hey, we're doing a lot of work inside battery limits, optimizing, we can do that. But what happens if we start integrating between companies and optimizing across them? And then, you know, we're having, as one of our scenarios, we drew it forward and saying, hey, you know, what's going to happen later on when the demand for carbon fuels is going to reduce? What's going to happen with these refineries? And that's a discussion that's ongoing at this moment.
Yeah.
And I think you're right that, you know, the modeling space is different. You can't just transpose it to that sort of equation. But we are driving those sort of discussions, and we are finding that by integrating industry more together, we can create a next layer of benefits.
Yes. Yeah.
One of the issues with that is competition law.
Right.
And so going back
Right,
to
right.
Carwi work, Carwi's not allowed to do that work.
Exactly.
Right.
So what technology
Everybody's
enables
still keen. Okay.
Talk about innovation.
technology
Yes.
enables certain amount of correct interaction and making sure the information shared is not improper and only the right people see it and make the right decisions from it. So that they're not deciding, okay, we're all going to, here we are in this particular region, we're just going to manage our gasoline production and we're going to go into import mode and throw the price up. So you can't do that, and obviously the markets wouldn't like it, the public wouldn't like it, and the governments wouldn't like it. So you've got to find a way. But the technology, the digital technology exists now that you can upload a heck of a lot of information without sharing it with everyone. You do it every day. We all do it every day when we're on social media, right? We're not sharing with everyone. We're only sharing the appropriate information with each other that we want to share. I know it's a hairy space, but it's sort of like that. It's you can share a lot of useful information without killing the market.
Okay, so we're going to need the digital architectures to be able to interface. We're going to need the sophistication of the models, but the granularity of the questions to work together. And we're going to need somebody to convene the information sharing with appropriate skill set.